Right, welcome back. So we started our discussion about shear and bending, and we talked about what these forces are and how to cut sections and all. Now, the rest of the things we are going to cover through this example. So we have this beam, and this beam is simply supported. So it has a roller on one end and it has a pin support on the other end. It is subjected to 2 point loads, one of them being 100 kips that is being applied at a distance of 3 feet from the lift support. And then if you move further at further 3 feet, you'll get to see another point load or concentrated force of 200 kips. The total length of the beam is 9 feet, as you can see. Now, again, if you're doing it on a paper, it's before you start the calculations, make sure that you dedicate a page for separately for the free body diagram and the shear force diagram and the bending moment diagram. I'm gonna show you all of that at the end. So, but you have to keep one page dedicated for that, for the drawings, you know. Again, like I've said, those would be the free body diagram, the shear force and the bending moment diagrams, and when you're starting off, you can draw the free body diagram in the beginning, and I'll show you how. So this is the free body diagram, a diagram that shows all of the active or acting forces and the reactive forces or the reactions on the beam. For now, I don't know the values of these reactions, so I can draw it this way. You don't need to have the supports when you're drawing the free body diagram, so you can remove this part and this part, but these are the action forces, the applied forces, the black ones, and the maroon ones are the reactions. For now, you can use these variables, but when you get to know the values, you can type equals to here and the values, so that would help. So in general, a free body diagram is the one that shows all of the applied forces in the body. Those forces could be the applied and the forces and the reactions, like I've said already, along with all of the distances as we have shown. Now, you need to know what sign convention we are going to follow when we want to draw the shear force and the bending moment diagram. Technically, you can go with any sign convention, but what most of the world does is they take rightwards forces as positive for the horizontal forces. For the vertical ones, it's upward, that's positive. And a lot of people would take counterclockwise positive. So that's what I'm going to take. Personally, I prefer going for clockwise, but that doesn't matter at all. But in this example, um, I'm going to follow the rest of the world. I'm going to take counterclockwise positive. Um, in future lectures, I'll tell you why I personally prefer to go for clockwise. But for now, let's go with this sign convention that is shown. So again, this is what I've said already, that this is not a hard and fast rule, and you can always go for some other sign convention of your choice. That's step one. When you start solving a beam for shear force and bending moment, the first step would be to find out the support reactions. And we have talked about it already that you'd be applying the three equations of equilibrium to find out the reactions. Um, Now, again, it's a matter of choice. A lot of people would start from some sigma fx or summation fx and then move on to fy and then moment. My personal preference is to start with the moment equation. The reason for that is when you start with the moment equation, you would always come up with one of the unknowns, and it makes finding out the reaction simpler. If I had started with summation fy, for example, I wouldn't have come up with a value. I would have come up with an equation that only had these two unknowns, ay and cy, and that would be of no use. So I personally prefer starting off with the moment equation. So I'll take sigma moment equals to 0, and I'm taking counterclockwise positive. Um, So my equation is since I'm taking moment about A. Oh, I have forgotten to mention that here, but I'm taking moment about A. When you're finding out the reactions, it's better to take moment about any of the two supports. So I'm going with A, and I'll write all of the forces along with their momentums. So this is the first example. So I'm showing this AY, but since AY acts at A, the distance of AY with respect to A is 0, and it's all right if I skip this force from my equation. But since this is the very first time I'm taking it into account, so AY into 0 minus 100, that's the first force that I come across. And the distance with respect to A for this force is 3. So it's 100 into 3, and I'm taking it minus because AY is going to rotate in this clockwise direction. And the next force that I come across is this 200 force. The distance of this force with respect to A is 3 plus 3, that is 6. And again, if I consider A as pivot, 200 is going to rotate clockwise. The last force that I come across is Cy, and the distance of Cy with respect to A is 3 plus 3 plus 3, that is 9, and the direction is clockwise, so I'll put a positive sign, and the summation of all of these should be equals to 0. Now, if I simplify, this is what I would come up with, and if you further simplify, you'll get Cy equals to 166.67 kips or kilopounds. Now, whatever unit system you're following, it doesn't matter. The procedure remains the same, whether you're using kips in pounds and feet, or you're using kilonewtons and meters. The procedure is going to be the same. Now, I'll move on to the next equation, and that's sigma Fy, and I'll take upwards as positive, like I've mentioned in the previous slide. Now, the first force I'm coming across, vertical force, is Ay. And that's going upwards, so I'll take that as positive. The next force that I come across is 100, and that's going downwards, so I'll take that as negative. Now the next force I come across is 200, and that's again going downwards, so I'll take a negative, and then the last force is Cy, and that's going upwards, so I'll put a positive sign. The summation of all of these would be 0. Now, since I have already worked out the value of Cy, I'll plug that in, and I'll come up with Ay. So Ay comes out to be 133.33 kips. I should have written the units here. I've forgotten, but you should not forget to put the units. Now all I'm left with is sigma fx equation. Again, I'm taking rightwards as positive, and if I start to write the equation, there is this one horizontal force, Ax, that's going rightwards, so I've put a positive sign, and had there been any other force, I would have added that here, but since there's no force, it's going to be 0 kips. So that's step 1, and I'm done with the reactions. Now I'll move on to the second step, that is cutting sections. And that has to be done at suitable locations. Once the section is cut, the portion of the structure would be made isolated from the whole structure, and that would be dealt separately. You'll see how we do that. The conditions of equilibrium are then applied to develop equations of equilibrium for each section. The thumb rule is that you have to cut a section before and after every force, or even a couple moment. If a distributed load exists, cut a section within the distributed load too. We'll talk about this later because this example doesn't have a distributed load. So for a point or concentrated load, the sections are to be cut before and after each force. A section is also required before and after the point where the orientation of the structure gets changed. So if you have a frame with multiple orientations, you are going to cut a section when the orientation changes, for example, from horizontal to vertical or the other way around. So let's talk about sections. The first section should be cut between this reactive force and this 100 force. So this is the first region that we're going to talk about. We'll call that section 1, and this is where the section is to be cut. The second section would be, since the first section was before this 100 kips force, the second one would be after this force. Okay, some of you might be wondering why I haven't cut a section before this force. That is because we don't have any span with before this force. Had there been any span before this force, we would have cut a section before this. So no section before this force because we don't have any space in one section after this. The same section is the one that is being cut before this force, and the second section would be the one that would be cut after this force. Now this section also becomes the section before this force, the 200 kips force, and for after the force section, we'll have to cut another section, that is section 3 here. Now this section is being cut after this force and before this 166.67 kilonewtons reaction, so there would be 3 sections in all. Excuse me, I just have sore throats and I had to record this video anyway, so whatever condition I have, I'm going to record this anyway. So let's talk about section 1. And when you cut this thing from here, this beam would be divided into 2 parts. One is this whole part, this part on the left, and the leftover part would be the other part. Now, it's totally your call to pick whatever part you like, but generally, we cut sections from the left. That's again not a hard and fast rule, but it's totally fine. Whatever you want to pick, but we would prefer going from the left. So if I pick this left part, this is what I get to see. I'll have this 133.33 reaction, and this much part of the beam. This is the cutting symbol, and since I've cut this beam here, the internal forces of the beam at this point are exposed, and there are 3 forces: the axial force, the shear force, and the bending moment. Now, I could have cut this beam anywhere between this point and this point, could be here or here or here or here. So this distance is not 3, it's something less than 3. And since this could be any random distance, I'm going to call this x. And we have talked about the limits already. So if I start from this point, the extreme left, this would be 0. If I add the 3 to that, this point would be 3. So the limits for the first section would be from 0 to 3. For the second section, this was 3 already. So if I add this 3 here, this becomes 6. The lower limit for second section would be 3, and the upper limit would be 6. And for the third one, the lower limit is 6. And if I add this 3 feet to that, I'll get the upper limit of this section, that would be 9. So the first section would have the limits from 0 to 3. X could be anywhere between 0 to 3. And let's start with summation of x equation. We are going to take again right versus force as positive. So there's only one horizontal force. A comes out to be 0. Now we'll go for Fy, and sigma Fy is 0. Upwards taken, the forces are taken positive. So if we add all of the vertical forces in the diagram, it's going to be 133.33. That's going upwards. And then V is going downward, the shear force, so I'll put a negative sign. The sum is going to be 0. Or if I simplify this, I'll come up with V equals to 133.33 kips. Now the last equation I'm taking is the moment equation, and the moment should always be taken about the point, the exact point where the beam is being cut. So this would be the point. Now when I'm taking this point as pivot, A and V would be having 0 distance with respect to this point, and that means they are not going to be a part of my equation. But this 133, since that has some significant distance, that is x, that would be creating moment, and this couple moment itself would be a part of the equation. So here it goes, and again I'm taking counterclockwise as positive. So it's 133.33. X is the distance from this point, and plus the moment, since that's going counterclockwise, is 0. If you simplify this, the first moment equation would be 133.33x. Now, so this is the point that about the circle point is the one about which we are taking the moment. Now, if we talk about the second section, the limits of that section would be from 3 to 6, like we've discussed in the previous lecture and then in the previous slide as well. This is what you get because you are getting the second section after the 100 Gibbs load. Now, the distance from 133 to 100 was 3, as obvious. The distance from the extreme left up to the point where the section is being cut is x. Some people would take this distance as x, and that is not wrong, but this is more convenient, so I'm going for this one. Now, if this whole distance is x and this one is 3, this leftover distance should be x minus 3. So I'll write that here. And again, you can see the internal forces being exposed, the axial one, the shear, and the moment. Again, we'll apply summation fx equals to 0. I'll go a bit quicker now. A is 0. I'll apply summation fy. I'll take upwards as positive. Now, whatever vertical force is there, I'm going to take them 133.33 upwards, minus 100. So I'll put it's downwards, so I'll put a negative sign, and minus v, the vertical force, shear force, equals to 0. And if I simplify, I'll get v equals to 33.33 kips. Now I'll apply moment equation and I'll take moment about this point, the point where the section is being cut. The first force I get to see is 133.33 and x is the distance. So I'll use that, and since this is going clockwise, I'll put a negative sign. The next force I can see is 100 and this distance is x minus 3. So I'll plug in the distance, and since this is going counterclockwise, I'll put a positive sign, and then this internal moment has the counterclockwise direction, so I'll take it positive and the summation is 0. So this is the point, the circle point is the one about which I'm taking the moment, and this is the moment equation in reduced form. I'll go for section 3. So this distance was 3, this was 3, this whole thing is x, this would be x minus this 3, so this is x minus 3, and this should be x minus 3 and minus 3 x or x minus 6. These are the distances. I'll go quickly now. Sigma fx is 0. Axial force would be 0 for Fy. 133.33 minus 100 minus 200 minus V equals 0. If you simplify that, you'll get V equals to minus 166.67. And you should notice that this value is the same as the last reaction. We'll talk about that later on. We'll apply summation moment equation and we'll use all of these forces and we'll plug in the relevant moment terms to get the moment equation. And these are the equations. Excuse me, I already have bad throat, but I had to record this lecture. So these are, you see the equations for the first, second, and third section. In the first line, we have shear and moment equation for the first section. Now what we have to do is we have to plot this graph between shear force and the distance and the bending moment versus distance. What we should do is we have to plug in the values. Since the shear equation for the first section is constant, it's independent of x. So if I put this 0 or 3 or whatever value here, it's going to be the same. But as far as this moment equation is concerned, if I put the lower value, that was 3 for the first section, I'll get 0. And if I plug in the upper value, that is 3 here, I'm going to get 400. So these are the values for the first section. In this line, we are going to talk about the second section. And again, we are going to put the lower and the upper limit in this. And again, if you see the second section's shear equation, it's a constant, so whether you put the lower limit or the upper limit of the section 3 or 6, you're going to get the same value. But for moment, if I plug in the lower limit, I'll get 400, and if I put the upper value, I'll get 500. You should notice that the value of moment from the first section at 3 is the same as the value of moment at the lower limit from the second section, which is again at 3. So we are getting the same values from two different equations at the same point. That is because we don't have any moment acting at the point. We are going to talk about this point in future lectures. Now that we're done with two of the sections, we move on to the last section. And again, for v, this is constant. So whatever value of x you would consider, 6 or 9 or anything in between, you're going to get the same value. And for a moment, when you plug in the lower limit, you're going to get 500, and which is again the same as the moment value from the previous equation at the same location. And if you plug in the upper limit 9, you are going to get 0. So it's always better to come up with this table. Some people won't go about this table, and that is totally fine as long as you have these values. Okay, so once we have this table for the values of shear and moment for each section, at least the lower and the upper limit, we'll draw the shear force bending moment diagrams. Some of you may ask, why didn't we took just two values for each section? That is because we have a linear equation for that, so two values is enough. The thumb rule is that the number of values that you require to plot a graph would be the highest power or order of the equation plus 1. So it's a linear equation, the highest power is 1. If you add 1 to that, you'll get 2, and 2 values is all you need for plotting this. Okay, the first step is to draw the free body diagram. I was a bit lazy to remove these supports, but otherwise, if you remove the supports, this is how the free body diagram should look like. Now we're going to draw the shear force and bending moment on the same scale. So this line represents 0, or it represents the beam, you could say. The horizontal axis shows the distance, just like here. So this point is 0 here. This is 3, so this is 3 here just below that. This is 3 plus 3, 6, so it's 6 here, and it's 9. So it's on the same scale. Now, if you see the first section, the lower limit, the shear at lower limit was 0, and it was at 3 at upper limit. So if I take a rough scale, this is like 300 on the y-axis. You plot at x equals to 0 at the start of the beam, the value is 133, and at the end of this section, at this location, the value is 133. If you join these two, you're going to get a straight line, and I'll write the value here, which is 133.33 at both the points. Now, if we move on to the second section, the value was reduced to 33.33, so I'll come here. It's 33.33 here and 33.33 here. If I can join these two with a straight line. And for the third section, and I have to write the values here, and then I'll go to the third section, which has 166.67 value, and again the same value. So this is how I would join them, and I'll write the values. Now you should know that these are supposed to be closed figures, so I'll close them, and this completes the shear force diagram. Now there is one thing that you need to observe, and that is, if you move from 0 to this point, this is 133.33, and so there's this vertical line of 133.33, and if you look at the free body diagram, you can see an upwards force of 133.33. So the line goes upwards, and the value is 133.33. This line actually shows that there is this vertical upward going force in the free body diagram. Now, if I move to this point, and if I see it was 133.33 at one point, and then it became 33.33, so the difference is 100. The line is moving downwards, and this shows, the reduction shows that there must be a downward force of 100 at this point in the free body diagram. Similarly, if you see at this point, this is 33, and if you neglect the sign, minus 166.67, you add these two, you'll get 200. This is going downwards, and this shows there should be point load of 200 kFs at this point on the free body diagram. And if you see here, it's 166.67, and it becomes 0. So The only way that can happen is when you add 166.67 to this, and that means there must be an upward going force from 166.67 at this point, which is there. So this justifies, and this is how you would check your diagram is correct or not. You should also notice that this value is equal to the reaction here, and this value is equal to the reaction here. Now let's move on to the bending moment diagram. Again, we're going to follow the same scale. So this is 0, this is 3, 6, and 9. At x equals to 0, the value is 0 moment, and for x equals to 3, the moment is 400. Now, if you join these 2 points with a straight line, this is what you get, and we'll write the values there. For the second section at lower limit, you again had the same value, and for the upper limit, you had the value 500. Again, if you join these two with a straight line, this is what you get, and I'll write the value here. For the third section, the lower limit has the value 500 and the upper limit has the value 0. So if you join these 2 points, you're going to get a straight line again, and you can write the values, and this completes the bending moment diagram. You can also see that this area is positive here, and this is positive, and as long as the shear diagram is in positive region, the lines are going upwards, and when this enters into negative regions, the value of bending moment starts to reduce. We talk about this thing in later on. We'll stop here for now.